So 5.1 was all about the derivative of the natural log. Okay? So if you remember, if we take derivative of natural log, what do we get? 1 over x. And in general, it's the derivative of the log argument over the argument. So what we're doing now is we're integrating. Okay? It's not that we're integrating natural log. It's that we're integrating 1 over x to get natural log. We're integrating a derivative over something else to get natural log. Okay? Notice these absolute value bars. What's that about?
Can't be negative.
What can't be negative?
The value is 0.
I'm about to sneeze. Hold on.
Oh.
No, it went away. Okay. Whenever you take natural log of something, you can only take natural log of positive numbers. It goes back to the domain. So that's why we put the absolute value bars around everything. There are times when you won't need the absolute value bars because of what's inside has to be positive. Think of this like x squared. Can x squared be negative?
Yes.
No.
Well, not in real numbers.
But it ends up being positive.
Yeah, that's what I'm saying.
Oh,
So
okay.
you don't need the absolute value bars, but they don't hurt either.
Okay, I got you.
Okay, so we're just going to put them, we're probably going to use absolute value bars maybe even more than we need to. Okay, so let's look at problem number 1. First of all, when you see numbers like this, it's best just to put them on the outside of the integration. It's going to make knowing what to do next easier. Either integrating the old way or integrating now using natural logs, getting that number out of the way. We've been used to doing that. And so this integrates just to natural log of x. And notice that I'm putting that x in absolute value bars. And then don't forget your plus c. We're back to integrating, so we need plus c at the end every time.
So the denominator is what goes in between the absolute values.
Yeah. Okay, so we look at 2, and really what we're looking for is where the numerator is the derivative of the denominator. It doesn't have to match up exactly. Like here, what's the derivative of the denominator? 5, okay? So anytime it gets a little weird, we just do a u substitution. We say u equals the denominator, 5x plus 3. Then du would be 5 dx. And we're used to this. What do we do with that 5? Move it over to the front. Okay, so what this then becomes is, I'm going to go ahead and write the 1/5 first. We've done this enough. You know that 1/5 is eventually going to go out in front of the integration symbol, so just move it out there. I'm going to move it out there early on. This becomes 1 over u du, which, just like the last problem, natural log of u, again, u is in absolute value bars. And I'm not done, though, because I started with x's, I need to end in x's. The only exception would be like a problem number 6 where you have numbers. You're not going to end in x or u, you're going to end with a number. All right, but if you start with x's, you got to end with x's. So 1/5 natural log of 5x plus 3 plus c.
If our answer doesn't have the absolute values, that would be bad, right?
You need to have it, yeah. It's not fully correct unless you have the absolute value bar there. All right, I'm going to switch from color to color because these are probably too close together. Probably should have allowed for more room here. Sorry about that. So looking at 3 and kind of following the pattern without thinking too far ahead, what do you think u should equal? The denominator, x squared plus 6x. So then du would be 2x plus 6 dx. But I don't see a 2x plus 6. And I can get there with one little tiny little step.
Multiply the numerator by 2.
I could multiply the numerator by 2, but something that would be a lot easier is just to divide this by 2.
Divide it. Okay.
So in other words, divide both sides by 2, and you get 1/2 du equals x plus 3 dx. And now you have this x plus 3 dx to substitute in 1/2 u. All right. So, from here, I'm gonna have to move it up here. I'm gonna put the 1/2 in front again. I know it's eventually gonna go out there, so I'm just gonna go ahead and put it out there. 1/u du. And notice that you get either 1/x dx or 1/u du. That's how you know this is a natural log. That's how you know that antiderivative is natural log. So 1/2 natural log u plus c. My final answer being 1/2 natural log. And then make sure you write your u correctly. And I'm going to do the rest of these on another sheet of paper so that I have more room and I can write bigger. Does that sound like a good plan to y'all? Okay. So I just get mine to look at. All right, so number 4, trig 1. Sometimes these are a lot more difficult. Most of the time, they just look more difficult, but you're still going to need to know your basic trig derivatives. Okay, so this is what I'm saying. I'm going to go ahead and just start writing them up here. Because I saw some of you squinting. Okay, so again, we're looking for, if I'm going to use natural log, I'm looking for where the numerator is the derivative of the denominator. Is that happening here? Yeah. In fact, if you weren't sure, just again, go ahead and let the denominator be u. That seems to be the trend here. Du then would equal secant squared x. You need to know these values. Nothing to divide, right? Because look, all of this is right here. There's nothing extra, there's nothing missing. So this becomes an integral 1/u du.
I have a question.
Yes,
Why doesn't it come du over u?
it could. You could write it this way. Same thing.
Okay, it's fine.
It's just, I'm writing it 1/u du because this is how we've already seen it.
Oh.
We typically have this du or dx off to the side, but it's just being multiplied, right? So it's the same thing.
Going to be how it is almost nothing. Or
You're eventually going to want to get to this if it's a natural log.
right.
But yes. So this becomes natural log of absolute value of u plus c. And then again, my beginning problem was an x, so I have to go back to x. And I have to go, u is equal to tan x, I have to put that in, and here's my answer. All right, now we've already worked 4 examples, and even though this one was trig, they've all been kind of similar. Okay? Commonalities include letting the denominator be u, noticing that you have the derivative there. We have the absolute value bars, we have the plus c, and there's a lot of things that happen on every problem, but it is a lot to remember. Okay, some of these, starting with the next one, they're going to get a little bit more difficult. Each one is going to have kind of like a tiny twist or turn involved in the problem. All right, so we've got to remember everything that we know about integration. And I know that's like that's a tall order to remember everything you know about integration. But the better you were at chapter 4, the easier all this stuff is going to be. Okay, so let's move on to 5. Oh, also, how could we check these answers?
Calculator.
We could integrate in the calculator. How could you do it without the calculator?
Find the derivative of your answer.
Yeah, find the derivative of the answer. So like in the end, whatever my answer is, if I take derivative, it should be 2x over x plus 1 squared. All right, so this one's a little bit different because it may not be so clear as to what x should be. What u should be. So I want y'all to watch what I'm doing here. If I let u just equal the whole denominator, which is what I had done on the previous examples, then du, I'm going to erase this, so don't write this down, okay? Just watch. Du would be, I'd move the 2 in front, I'd have the x plus 1, go down by 1, okay? Multiply it to the inside, and then really this is 2x plus 2, but I only have a 2x. So there is a way out of this, but you don't want to know what it is, okay? What's going to be way better instead is just to remember our original rule about what you let u equal.
What's under the x?
What's in parentheses being taken to a power, okay? Let's still use that. Okay, so then we let du equal dx. And so now instead of having too much, I'm actually missing something. But we do know we already have some way to take care of that, right? Okay, so let's go ahead and look at what we have here. Let's go ahead and move the 2 out to the front, first of all. And in place of x plus 1, let's write the u. So u squared instead of dx, let's write du. And what we have left over is that x right there. And when we have an x left over, what type of problem is this? It's a TOCO problem, which means we've got to solve for x. So what would x equal?
U minus 1.
U minus 1. Okay. So u minus 1 goes right here. The nice thing about TOCOs is a lot of times they, or I, whoever's giving you the problem, doesn't really make you finish it. So it could be that this is as far as you need to go. Okay? Okay, so, but I want to go ahead and finish this because there's a really good other strategy that comes up. Alright, on the TOCO problems before, we would have like, usually it was like the square root of u in the denominator. That happened a lot. Here it's u squared. I could move u to the -2 up top and distribute. And if you feel comfortable with doing that, do that. I'm going to approach this one a little bit differently, just to prove a point. When your denominator, anytime your denominator is just one thing, you can split it apart, basically uncombined terms. All right, you can only do this when your denominator is what we call a monomial. It's one term. Yeah, it's being squared, but there's no pluses or minuses. Okay, what this is going to allow us to do is to split this up into 2 integrals. And this is the this is what I really wanted to show on this problem after the TOCO. Okay, notice that the 2 went with both pieces. I could have done 2 in a big bracket, but we had one big messy integral, okay, and then I broke it up into 2 smaller pieces. Again, we've seen this with the TOCOs before. Any questions so far?
This would make it really bad if we had to evaluate it. We don't have to evaluate it.
Well, if you had to evaluate this one, you would have had to change your bounds, but we still have to integrate first before we evaluate anyway. Yeah, that would be a lot of problems.
Yeah.
One thing. Okay, so I'm going to simplify this. And I'm going to rewrite this one as u to the -2. I didn't write this one as u to the -1. Let me extend this so you can see better. But I left it as 1 over u du because that's how we usually see the natural log. This one over here, though, is not a natural log. Okay, it's only 1 over u is natural log. If you have any other power, that means that this could have been in the last chapter test. So remember, with these, you add 1 to the power, and you put the reciprocal in front. And I'm just going to put a single plus c at the end. Remember, c is a constant, so you don't have to write plus c over here and then plus c over here and treat them differently. It's just there's a constant added at the end. I don't know what it is. I don't even have enough information to find it. And it's going to change anyway when I now go into x. So here, what was u representing? X plus 1? -2 times -1, that's +2. I do want you to notice that I'm not putting this x plus 1 in absolute value bars because it's not linked to a logarithm.
So does C represent both C's then?
It just represents at the end of this, there's some plus number. That number is changing as I go throughout the entire problem. In particular, it changed a big time when I went from U to X. So it's changing all the time. So there's no need to put like plus 2C or anything like that.
Well, I was just saying, since you integrated twice, there should be 2. If you could just divide the four
Yeah,
times.
2 times a number is still a number.
Okay.
Okay, so that one was a lot of steps. So we're not going to have to do that many steps in one problem. But it's good to know each piece. Okay, let's look at, what's next? 6. Okay, this one does have bounds. So we know we have some bounds. So if I go into U substitution, I'm going to have to change those numbers. Do you think we need U substitution? If the answer is no, then you got to tell me how we're going to integrate it.
Yes.
Divide it up.
Well, we can't break this up because the denominator is not a monomial.
Oh, okay.
Like if it had been the other way around, like where the x squared plus 1 was on top over x, I could have simplified each piece, and that would have for sure been an easier way to do it. But when your denominator is something like this, that's your u. And what we're hoping is that our du is there. Okay, we definitely don't want too much over here. And if I don't have enough, well then that's a TOCO problem. So it looks like I have too much, but there's an easy fix to it, right? The numbers we can just divide out. Okay, but like when I say too much, if this had been x squared, there's no way to deal with that. Okay? So here's x dx, here's x dx. This is why this is the perfect problem. I don't mean to say perfect, but I mean, it's not a TOCO, it's not anything else that's weird. So let's go ahead and change our numbers at the same time, 3 and 0. So remember, these numbers right now are x's, because they're in the original problem. So I gotta square them and add 1. So what is the 3 gonna become? 10, and the 0 becomes 1. Okay, these are u numbers. So once I go into u, I use these numbers, and I never go back to x. I'm going to go ahead and put the 1/2 in the front. Also, what I noticed last time, some people like to plug the numbers in immediately. You still have to integrate. You still have to integrate before you plug the numbers in. Okay, so don't go back to the old numbers. And also, you don't need to plug in x squared plus 1 back in for u. When you have bounds, as long as you've changed your bounds, stay in u notation. So this becomes natural log of 10 minus, and then plug in 1, natural log of 1. And I dropped the absolute value bars. Do you think that's okay? Do you need absolute value bars around 10 to know that it's positive? No, it's not a variable anymore. If you wrote absolute value bars, that would be okay, because the absolute value of 10 is 10. All right, but you're typically not going to see them around numbers like that. Okay, one of these logs we know. Which one do we know we can evaluate?
Oh, 1.
Yeah, natural log of 1, that's 0. And so 1/2 natural log of 10 is a great answer. I'm going to challenge you just a little bit to think of one more way to write this answer.
ln 10 over 2.
You're close. Natural log of something.
ln
10 to the 1/2, and probably like on a multiple choice test would be written like this. Square root of 10.
Oh, right.
So I want you to see what happened here. We took the 1/2 and we made it become the power on 10. The only reason I'm even saying is, what if this was the multiple choice answer? Okay, you just need to make sure that you know how to get that far if necessary. I would never expect you all to do this. Okay, that's why I boxed this. This is This first one that I wrote is perfectly acceptable. Okay, and so that's how you do one with bounds, very similar to what we did before. Okay, moving on. Number 7. Okay, number 7 is also a little bit different, because if I look at 7, it doesn't really seem that the denominator and the numerator, there's no like derivative. They're kind of almost the same. And so I want you to watch what I'm going to do here. Don't write this down. But if you just kind of go with what we did, and you say, okay, let u be the denominator, because sometimes you're not really sure what to do, so you just got to try something. Then du would be 2x dx. And sure, I could divide by the 2, but how on earth am I going to get this? Well, you might be thinking, okay, that's a TOCO, but this is even more complicated than a TOCO, because it's not like, look, how are you going to solve for x? That's going to be like u minus 1 and the square root of that. This is really complicated, okay? So we're going to have to really think outside the box on this one. This is, once I tell you what we do, some of you are going to whine a little bit, but then you'll get over it.
Factor.
Okay, so if we could factor and something could cancel, that would be great. Although it doesn't happen in this case. So if the denominator, let me just put this out here. If the denominator didn't have the plus 1, what could we do?
We could separate it because it's a denominator.
We could put each thing over x squared, simplify them, and go from there. So that could have been a problem. We already kind of did one like that. All right, but we can't just say, oh, it'd be nice if the plus 1 wasn't there. I mean, it's there. We got to deal with it. So we're going to do something else. When you put everything over x squared, that's dividing. So we're actually going to do long division on this. Now, I will tell you that these long divisions are not the hardest of the long divisions you remember from pre-calc. Okay, so I want to do a really simple example first of long division. Okay, this is like 2nd, 3rd grade, depending on which school you went to. Okay, you can do this. Maybe 4th, I don't know. It's elementary school, like serious elementary school. So the first step with long division is to divide. All right, I'm going to write this down here. Divide. And you may want to write this like down at the bottom on another sheet. I realize I did not leave you that much space to do this, and I apologize. So we divide. We go 2 into 1. Okay, that didn't work. So 2 into 15. 7. And then what do you do?
Subtract 14.
Well, first we multiply to get 14. So we multiply. 7 times 2 is 14. Then I heard it. Subtract.
Drop your 3.
Yeah. I'm writing these steps down for a reason. You get 1 and then you bring down, right?
Right.
Then you just repeat. Okay, and so you go 2 goes into 13, that's the divide. 6. 6 times 2, multiply, is 12. Then you subtract the 12. There's nothing left to bring down. That's how you know you're done. And what do we call this one?
Remainder.
We call it a remainder. And if I wanted to rewrite 7, if I wanted to write it up here, I could do decimals, but the very first way you did this was to just go and 1/2. The remainder is 1 out of 2, so 1/2. So what it does is it rewrites 153 over 2 into a mixed number. This is what you're doing when you're doing long division with polynomials, okay? Everybody clear on this? Because I'm about to erase this, and we're going to do a polynomial example. Like I said, these can get really hairy, but the ones you're going to see in here are typically not going to be very messy. The only thing I suggest is when you're writing the denominator or the numerator and there's a missing term, like x, is to write 0x. Y'all remember that?
Yeah.
That's going to make everything line up better if you do it that way. And then the numerator goes up right here. And again, if any of these terms were missing, we would put plus 0, whatever. And we're going to go through the steps: divide, multiply, subtract, bring down. Okay, so when you divide, just look at the leading terms. X squared goes into x squared how many times? Once. 1 times x squared, 1 times 0x, 1 times 1. That's the multiply. So we divided, we multiplied, and now we got to subtract. And when you subtract, really, it's easier just to change all these to minuses. You could put minus parenthesis, but, and then let's see what cancels. And if we need to bring down, we bring down. That's not going to be an issue on this one. So 1 minus 1 even cancels. And the only thing I'm left with is this tiny little x. And we call that our remainder. By the way, if you get no remainder, that's even better. That makes your life way easier. And that means that probably this factored
Yeah.
and you just missed it. All right? And so the way we're going to write this is we're going to write 1 plus my remainder over whatever the denominator was. So all that work, although it really wasn't that much work, I mean, it was kind of like old and maybe we've forgotten about it, but it's not that much work to do the long division. And on these types of problems, the long division is not going to be that. It's going to be pretty easy like this. It may be a little bit harder, but not much. Okay, any questions on that?
How did you notice the x got over the 20?
It's for the same reason. After I got 76 and I got a remainder of 1, I put it over whatever I was dividing by. It's for that same reason. I have x left over, and then the denominator has to still be that same thing. All right, so this still looks kind of complicated, so let's break this up. And so let's integrate 1 dx, and let's add that to integrating x over x squared plus 1 dx. So let's take it from one big piece to 2 smaller pieces. And the biggest question you may be asking yourself now, or you will for sure later, is how do you know when to do what? A lot of this is you have a big toolbox, you have a lot of things to try. If you try something and it doesn't work, you try something else. And the more you do it, the better you get. You'll start to see patterns. So integrating 1, what's that? What's the antiderivative of 1?
1/2 x.
Just x.
You're just that, sorry.
Right. And I didn't have to do u substitution or anything. Now to do the second piece, I am going to have to do u substitution. This one piece is really like problem 2 or 3. Okay, so we're going to have to go off to the side and do the u substitution. Let the denominator be u. Let's hope this works out. If it doesn't, we'll all just go home. And it looks like it is going to work out because x dx, there's not too much, there's enough, it all works out. Okay, so let's go ahead and put the 1/2 that's in front of the du. Let's put that in front of the integral. And then I have 1 over u du. I know this is a lot of steps. I get it. It's going to take us a few days to get better at this. Okay, so let's see. Not because of this one, but because of that one. It doesn't really matter. As long as we put a plus c at the end, we're good. Okay, so this is going to be natural log of u with absolute value bars. And then you got to just keep going until you get all the way back to x's. There you go. One thing about these is if you were to check this by taking the derivative, it would not lead you back to the original. It would lead you to right here. So it's important that you can do long division, because that's not something you can really check very well. Alright, I will say that I think these are the hardest types, so the next two are going to seem really easy. Alright, I've said this a lot of times, but really the hardest thing about these is knowing what to let u equal. And again, if you let u equal something and you're going to get a dead end, then you need to pick the right u. You need to go back and pick a different u. This is why it's important to practice, because that's I can teach you all the different ways to look for you, but it's something you kind of have to work out on your own a little bit.
If you said ln x to that derivative of that is 1 over x, right?
Yeah, so if I let u equal natural log of x, then du, although it's not in the numerator, 1 over x dx, it's right there.
Yep.
Okay, what would be the problem with possibly setting the whole denominator equal to u, which is kind of what I did on most of the others? Why would that not work?
X to the x.
Yeah, x to the x is the problem, but like, look, if u is x, natural log x, du is really complicated, right? It's product rule. And you're going to have some things here that you can't account for, okay? And you don't want to have too much. So this is going to simplify. Again, just once you let your u, once you have the correct u, in other words, things fall into place. That's just natural log of u. Let's see. And then this next thing is really going to bother some of you, because you're going to get natural log of x. And you're going to say, you can take natural log of natural log? Well, I guess you can, because here it is. When would that really happen in real life? Well, there's a reason why natural log of natural log is. There are times, but we're really not ready for that even. We need to practice these skills first. Okay? I want to go back to 7 just really quick, not to make anybody feel bad about how long this problem was, but do you think I really need those absolute value bars around x squared plus 1?
No, because you know it's positive.
X squared plus 1 has to be positive. So you could have left them off. Now, most of you, like me, are never going to really think that. I mean, I didn't until I was like, oh yeah, I forgot about that. And this is my 3rd time doing this problem today alone. So just put the absolute value bars on. Really, you don't need to worry about when you need them and when you don't, okay? But I know some of you are thinking that, so I wanted to put it out there. All right, last problem. Integrating tan x. Seems like this is something we should have already done, but we haven't, right? Remember that this thing right here is the derivative. Tan x isn't the derivative of anything we've seen before. We know how to take the derivative of tan x and get secant squared. I know how to take the derivative of secant and get tan secant, but this integral alone we've never done before. Okay? So you might be thinking, well, let u be tan x. I've told you this, you don't ever want to let your whole integral be u. If that's the case, then you didn't need u substitution. So what we need to do instead is think, okay, I had fractions on every other problem. Maybe rewriting this as a fraction, maybe it'll make it more obvious. So how can you rewrite tangent?
Sine over cosine.
Sine x over cosine x. And if one of these is the derivative of the other, then we're on the right track. Okay, so what do you think u should equal?
Sine x.
Cosine. It's not that cosine is more important, it's that cosine's in the denominator. Right? We want u to be in the denominator. So then that would be negative sine x dx. I can move that negative to the other side, and that's really just going to become a negative in front, just like a 1/2 or any other number. Okay, now remember, sine x dx, we got to make sure that's there. It is there. That whole thing is being replaced with du. Specifically negative du, but we're going to move the negative out here. So you just get 1 over u du. I mean, you notice how it's like crazy, and then it just goes 1 over u du. That's how you know you're doing it right when that happens. So then I have negative natural log, absolute value bars of u, plus c. And then one more step to take it back into x. All right, now this really wasn't too many steps, and if you saw this again, you could do it. From now on, if you memorize this, then you can use this. You don't have to go through any steps. So I want you to look at the box that's at the bottom of your paper.
Second.
Yeah, it's this one right here. That's the one we just did. Eventually, you are going to have to memorize this. There's not a lot of things I want you to memorize in here, but these are some things you're going to have to do. I'm going to give you some cards to help you remember it. You already know these two, or you should. Those top two we already did. All right? If you were doing cotangent by hand, what would you change cotangent to? 1 over tan,
It's just cosine over sine.
which is cosine over sine, and your u would then be sine x, okay? So, like, for now, if you're like, I don't want to memorize these, you can do them by hand. They're really not that hard. Now, the bottom row is a little bit more difficult because, think about this. What's secant? 1 over cosine. What you would have to do is replace that 1 with the Pythagorean identity, sine squared plus cosine squared. And then you'd have to split it up, and you'd have to simplify, and you'd have to go from there. So it's kind of like, you might think, well, I'm not going to memorize. At some point, you're going to want to memorize. All right? That's not going to happen today. It's not going to happen in 2 days. It's going to take a while for us to get there, okay?